Am I audible?
Yeah.
Okay. We'll start the session today. Welcome. Welcome to this tutorial session for the course Computational Fluid Dynamics offered by Professor Srinivas Jayanti. I'm Sankar H. I'll be your teaching assistant for the day. And we'll go through some of the lectures, some of the questions that were discussed in the graded and non-graded assignments of week number 9, which mainly deals with the solution of system of equations. Now let's get started with the graded assignments of the previous week, which, excuse me for that, yeah, we'll start with the graded assignments for the previous week, which deals with the solution of Laplace equation in the three-dimensional domain, and which spans the length of L in the x direction, W in the y direction, and H in the z direction. Now, according to the statement that's been given, we have divided the length into 40 equal intervals, the width into 30 equal intervals, and the height into 25 equal intervals. We have Dirichlet boundary condition on all sides. We discretize the Laplace equation using a central difference approximation and wish to solve the resulting set of linear algebraic equations, which you have expressed in the matrix form as Ax equal to q with lexicographic ordering. For this problem, we have to answer a set of equations. So let's start by drawing or figuratively representing our equation or the question that's given. There is a three-dimensional domain that's given. Let's call this as x, this as y, this as z maybe, and we have a Laplace equation that's in this domain. So let's take the property in consideration to be phi. So according to the Laplace operation, we'll get del square phi is maybe some function f. Uh, this is
It is zero,
basically
right?
what's, sorry?
That should be zero, isn't it? Laplace.
Oh yeah, sorry. Yeah, it should be 0. Actually, Laplace equation just needs to be function, right? Poisson equation is what needs to be 0, or am I wrong there?
No, it's the other way around.
Okay, right. Fine. Regardless, if it's 0, we just, even if it's the other way, it's okay. Now we'll put this in, we'll expand this del square phi. Since we have written this as del square, we'll write this as dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square should be equal to 0. Now we discretize this using central difference method, which can be written down as phi I I plus 1 j k minus 2 phi I j k plus phi I minus 1 j k by delta x square plus phi I j plus 1 k minus 2 phi I j k plus phi I j minus 1 k by delta y square plus phi I j k plus 1 minus 2 phi I j k plus phi I j k minus 1 by delta y square should be equal to 0. Now we are going to answer based on this much whatever we have done. So what we can also see is that we have to discretize this into
Last one is z squared, by the way. It's been
sorry, yeah,
a typo, yeah.
sorry, yeah. So what we have done is basically we have split the domain into in the x direction we have split it into 40 equal intervals. We have split the y direction, the width into 30 different intervals. We have split, let's say, the z direction in in the 25 different intervals. So from each of this will be get, if you have divided into n points, n intervals, we'll get n plus 1 point. So basically if you have divided line into 2 intervals, we'll get 1 2 3 points. So interval 1, interval 2 will get 3 points. So if we have n different intervals, we'll get n plus 1 points. Now, based on whatever you have done, we'll go on to answer the questions what have come up in the question and the assignments. Which of the following are true about matrix A? First point is it will have 9 non-zero diagonal elements. Second one, more than 99.9% of the elements of A will be 0. Third one, it will satisfy this kind of strong form of diagonal dominance. So based on whatever we have written, what we are going to do, let me just finish this, whatever I have been telling here, is that what we have got is an equation with 1, 2, 3, 4, 5, 6, 7 variables. These three are the same. So we have one, let me make a note of that, we use a different color. So we have 1, 2, 3, 4, 5, 6, 7 elements. One second, just figuring out some stuff over here. Yeah, so we have 7 elements in each equation. So the first statement is it will have non-zero diagonals. Basically, whenever we are talking about the element I, j, k, it will be the diagonal element, whereas the other ones I plus 1, j plus 1 or k plus or minus 1 will be the non-diagonal elements. And we can see here that we have exactly 6 non-diagonal elements. So when we write this in the lexicographic notation, we'll be writing this as let's for example take the first equation to be 5 1 sorry 5211 minus 2511 plus 5 one second, 1 will not be there, so we'll be starting from n equal to 2 to n equal to n minus 1, or I equal to 2, ijk equal to 2 to ijk equal to l minus 1. We'll be getting that as 5 3 2 2 minus 2 5 2 2 2 plus 5 1 2 2 2 divided by delta x square. And similarly we'll get 2 3 2 here, 2 2 2 here, and 2 1 2 here for delta y square, and 2 2 3 2 2 2 and 2 2 1 for delta z square. So when we put them in the matrix form and write all of them, we'll get that all the 5 1 1 1 5 1 1 2 sorry 2 1 1 etc up to 5 let's me call it as ljk, or the ending of that ijk or whatever it is will be written in this form, and we'll be equating that to a zero matrix as shown here. So when we solve such an equation, we'll be getting the from that we'll see that we have not 9 non-zero diagonals. We saw that it was in fact 6 non-zero diagonals at max, and therefore this statement is invalid. Now second statement, more than 99.9% of the elements will be 0. So we see that in each equation we'll have a maximum of 7 elements, and there will be totally around the total number of, we'll come back to the second question once we do a further question, and the third one will be, it will satisfy the strong form of diagonal dominance. And what we see here is that if from the solution of these terms we we will get the strong form of diagonal dominance if this delta x, delta y and delta z are same. Otherwise we cannot guarantee that all these I, j, k and I plus 1 or j plus or minus 1 or k plus or minus 1 will be greater than or less than or equal to I, j, k. So therefore we can't say anything about the strong form of diagonal dominance at the about this. And moreover, if you are taking an equation at the edges, if we consider the boundary condition that, let's say if you are doing it over the equation that I have shown here, we know that phi 1 2 2, phi 2 1 2 and phi 2 2 1 etc. are in fact known values because of the Dirichlet boundary condition. Therefore when we substitute these values, we see that these are obeying the strong form of the sorry and obeying the strong form of diagonal dominance. Whereas if we have a center point or interior point, we see that it will be obeying the weak form of the diagonal dominance, wherein if we can equate the sum of the coefficients over here to this one. So therefore this statement is true only for interior points and not boundary points.
So even though delta x, delta y, delta z are different, huh?
Yeah,
Despite that.
even though, yeah. So we can do, I'll just
Okay.
explain that
Okay.
then if you want.
Yeah.
So let's take a point which considers the boundary of x. We can write that as this particular this is the first point we have taken. Let's assume this is the first point we have taken.
That's an interior point. Yeah.
No, this is not an interior point, this is a boundary point, because one second, we have written it like this. So we see that the point 1 over here refers to a wall.
Oh, one. Oh, we have started from one. Oh, okay.
So
No, I thought we
basically,
started zero. Okay.
no. Basically, when we discretize, we don't consider zero into the number while numbering here.
Okay. Okay.
So basically, when we are writing it down, this will be the 1.234.
Okay.
Similarly, for y-axis will be 1 2 3. Here will be 1
Okay.
2 3, etc. So if we consider a point 2 2 2 and discretize at 2 2 2, that's what I've done here. Phi 2 2 2 is being taken as a point and discretized over there. We see that the strong form is obeyed because these three terms are known values, are basically constants. So the coefficient of all the non-diagonal elements will be uh, will be less than the diagonal elements over here. It'll be like this. I mean, some of the coefficients of the non-diagonal elements will be greater than the coefficient of the diagonal element in this case. Whereas if we take an interior point such as, let's say, 5 5 5, we'll get 6 5 5 minus 2 5 5 5 plus 5 it'll be 4 5 5. Similarly, if we do this is for delta x square. If we do it for delta y square, we'll get 5 6 5 minus 2 5 5 5 plus 5 4 5 by delta y square. And for z, you'll get 5 5 6 minus 2 5 5 5 plus 5 5 4 by delta z square. So we can see that none of these points are in fact known values from whatever you are doing. So all of these constants have to be equated, and we see that when we write them in the matrix form, we'll get the sum of the coefficients of the non-diagonal elements to be uh, 2 by delta x square plus 2 by delta y square plus 2 by delta z square, and the uh, coefficients of uh, the diagonal elements will be just the negative of that, minus 2 by delta x square plus minus 2 by delta y square minus 2 by delta z square. So we see that the magnitude of the sum of the coefficients of this is basically 1 by delta x square plus 1 by delta. So when we equate, we'll be able to equate this. Therefore, it won't satisfy the strong form of the diagonal dominance as asked over here. I'll come back to statement 2 because it can be further. One of the further questions asked after this will require a solution of that. Moving on to question number 2, which of the following are true about the matrix Q? So basically, what is matrix Q here? According to the question, they have written the express the matrix in the form Ax equal to Q, and so this matrix over here will be Q. This will not necessarily be 0, it will be having some values as well, and this matrix is Ax is equal to Q. So what can we say about this matrix Q? It is a square matrix. Again, when we solve for Ax, if this is an n by n matrix, this has to be an n by 1 matrix. So when we solve this, we'll be in fact getting an n by 1 matrix. Therefore, Q is not a square matrix. It is in fact a n by 1 matrix. All its elements have the same value. That's not necessarily the same, because we see that most of the values do go to 0, but if you have a boundary point as shown here, which, let's say, suppose the temperature over here is 30, 20 and 40, so in each of these walls we have to write down that minus 30, minus 40, whatever it be. So therefore its value is not the same. All its elements will not be the same. It depends on the boundary conditions that's being used. And third one is all the elements are negative real numbers. Again, that also depends on the boundary conditions that is being used. Suppose I have here, instead of 30, I'll have minus 30 and minus 20, minus 40. Again, when you take it to the right side, we'll be getting the positive values. So it need not necessarily be a negative real number. It can be a positive number as well. So let me just write that down, that this kind of statements depends on the boundary condition that is being used here. Okay, moving on to question number 3. The number of equations that needs to be solved is, so let's first find out the number of grid points under discussion, and that will be equal to, since there are 30 since there are 40 intervals in x, 30 intervals in y and 25 intervals in z, we'll get 41 grid points here, for 31 grid points here and 26 grid points here. Therefore, total number of grid points will be basically the arithmetic multiplication of these individual number of grid points, and finally we'll get the total number of grid points. We can calculate maybe 33,000 we'll get approximately. Let me just find out the exact number over here. It will be 33,046 grid points. Now, since there will be 33,046 grid points, what we know is, we know the function value at the end or the faces of each of these problems. So uh, one second. So when I consider uh, the system under study, we'll see that all of these faces will have a value that's already known, but only the interior points or the points that do not include the boundary are to be considered or have to be excluded from this while writing down. Since we already know the points and the boundaries, we have to exclude them. So how do we find the number of points in each of this faces is very simple over here. We just take the number of points in this, number of points in this, and multiply it twice since they are identical on the other side as well, and do that for all the faces in consideration, and we'll get the number of points that we need to avoid or exclude because they are the boundary points. Therefore, boundary points, let's say in the xy direction, should be equal to uh, 41 times 31 times 2, and boundary point in the yz direction will be 41 times 26 times 2, and xz will be 41 times, sorry, 31 times 26 times 2. So therefore, number of unknowns or what grid points need to be considered here. Unknown grid points will be equal to this 33,046 minus uh, sum of the boundary points in all phases, which is will the number that you obtain by subtracting the sum of these three from 33,046 will be the final answer. And if you do a quick calculation, we'll get the answer to be roughly 26,760 if I'm not wrong. So the option close to 27,000 is the right answer. Okay, let me move back to the point that I wanted to make earlier here. More than well, let's check whether how many elements of them will be or will not be 0. We see that there are a total of 26,760 equations or grid points that needs to be solved, and each equation will have at most 7 elements, and a total of 26,760 of grid points will be solved together. Sorry, one second, please. Let me think this through. I think I have made a mistake over here while explaining this. So when we solve for the 5 values over here, we see that in each of these equations there will be at most 7 elements, and each of these equations will contain the all the elements in this 27,760 elements. Therefore, totally there will be 7 elements out of the 26,760 elements which are non-zero. Therefore, 1 minus 7 by 26,760 will be 0, and we can see that this value times 100 percentage will be obviously sorry, that statement is correct. More than 99.9% of A will be 0. Yeah, we'll get this to be approximately 99.973%. So in each equation there will be 26,760 unknowns, but 7 will be non-zero. At max, I mean that statement also will be there. Okay, in the next question, fourth question, where in the coefficient matrix A, what percentage of number of rows will have the diagonal elements to be equal in magnitude to the sum of magnitudes of the off diagonal elements? So basically they have asked how many rows. This can be rephrased as follows: how many rows will be or will not be strictly the diagonally dominant. And we saw from the example I told earlier here that if the boundary points are considered, they will be strictly diagonally dominant, otherwise they won't be strictly diagonally dominant. And that we can evaluate by just finding out, oh excuse me, finding out the number of points which considers, or let me just rephrase that, the number of interior points divided by total number. And the interior points, when I say interior points, I mean that a point which does not have the function value known around it. So suppose this is the x, y and z axis. If the boundaries are not present any of the around any of the points around it, then we can call that as an interior point. Otherwise it's just an unknown or grid point, and that can be found out easily by considering the faces of the rows over here. So let me just make a statement. Okay, at this point I'd like to ask someone from the audience to tell how the solution has been arrived here, because I am slightly confused at this question here. I mean, let me just compare my notes with yours for a second. Mr. Sridhar, would you like to answer?
I got it wrong,
Yes.
though I thought it was 99.9, but apparently the answer is 90%. I couldn't figure out how.
Okay, fine. And what about Manju? Manju, are you there? Okay. So what I figured out was that,
I mean, there's no way I could get 90% because that's a huge number, no? 90%.
yeah. So basically what I think is, so the number of interior points divided by total number of points will be the rows, or total number of non-interior points. I'll just make that statement.
So by interior points, you mean other than boundary, correct?
No, other than, I mean all the points which do not consider the boundary in the equation. Okay, so let me put it
Oh,
this
okay.
way. Let
Okay.
me put it this way. Yeah, so I
So
have
yeah.
discretized here like this. So here only one interior point will be there. This one has a boundary over here. This one has a boundary here.
Oh,
Similarly, there will be only one interior point here.
oh, okay. So basically surrounded by unknowns.
Yeah. So let's take this case. This will
Yeah.
have one interior. This will have one equation among nine equations, right?
Yes.
Which will be a strictly dominant. Yes, so
No,
this will be the equation that comes with this will be strictly dominant. Here it won't be strictly dominant. Am
I
I
didn't get that. I mean, why is that
okay?
strictly dominant?
Okay, I'll write down the equation 1, 2, 3, 4, 5. 1, sorry, 1, 2, 3, 4, 5. So let's write the equation for, let's say, 2, 2
Two,
and
two.
here
Yeah.
3, 3.
Yeah.
So t 1 2 minus 2 t 2 2 plus t 2 3, sorry,
You're going in the y direction.
no, this is the x direction, right?
Okay.
Delta
Okay.
x square plus t 2 3 minus 2 t 2 2 plus t 2 1 by delta y square should be equal to 0. Yes, so
Yeah. Yeah.
let us assume that the temperature here is 20 degrees C, 10 degrees C. Let's take here it as 40 degrees C, and let's say go here as 50 degrees Celsius. Okay, so
Yeah.
when I solve this T12, that is the point here, T12 is known, and that is 40 minus 2T22 minus plus T32 by delta x square. Let's assume that delta x square is 1 and delta y square also is 1 for the sake of simplicity.
Hmm.
Then if we take this point T23, we don't know that. T22, we don't know that, but T21 we know. Okay, I guess small mistake over here. It's not 40 here. It'll be, since we are going in the x direction here, this point has to be considered over here. So 20 here and 40, T23 minus 2T22 plus 40 should be equal to 0, assuming delta x equal to delta y equal to 1. Is
Three,
this
two,
statement
one. Yeah.
okay?
Okay.
So when we solve this, when we put this in a matrix form, we'll get minus 4T22 plus T32 plus T23 equal to 0. And this will be the, what do you say,
Right.
the diagonal element over here.
Yeah. Okay.
So in this statement, in this particular element, in this particular row, we'll get that the coefficient of this one and this one is much less than the
Yeah.
coefficient here. Therefore, here diagonal dominance.
So any point that is touched by a boundary
Mm.
is diagonally dominant, right?
For a Dirichlet boundary condition.
Dirichlet, sorry.
Yeah. For a Dirichlet boundary condition, any point that is close to the boundary will be diagonally dominant. Let's
Bas-
take the
ba-
same. Sorry.
Basically adjacent, yeah.
Yeah.
So all the
Um,
adjacent points,
yeah. Yes. Yes. Adjacent. All the adjacent points to the boundary is will be the diagonally
diagonally
dominant.
dominant.
Yes.
Okay.
So let me take one more point in the center. T33 will take. So uh, just to make that clear, it will be T43 minus 2T33
They will
plus.
be equal, right? Because you don't know any of them.
Yes, we don't know any of the points.
So
We
the
don't know what
minus two,
T43.
yeah,
Yeah,
yeah, yeah,
exactly.
yeah,
We don't know any of
yeah.
1, 2, 3, 4, and we take the sum 1 plus 1 plus 1 plus 1 will be equal to the 4 over here. So, so what I am trying to say is the number of interior points will be given by, let's take this particular case right now. It will be number of interior points will be given by the total number of grid points minus 2 from each side multiplied by total number of grid points here minus 2 from each side. So if we have a three-dimensional, we just have to do it thrice. So
Yeah.
basically, if we have 31 grid points, we'll have 29 over here. And if we have, sorry, what is the first one? 40, right? So it will be 41 grid points will have 39 under consideration. 30 grid points will have 20. Sorry, not 30 again. It will be small mistakes. So 31 grid points will have 29. 26 will have 24. So if we take the ratio of this, basically this times this, the other way, 41, 31, 26, we'll get the number of rows that uh, are not strictly diagonally dominant. Is this statement okay? Do I need to rephrase anything?
Yeah, basically they are equal, correct?
Yes,
The
equal
coefficient,
in
yeah,
yeah,
off
yeah.
diagonal, yeah.
So let me just check it out first, or whether I have made a mistake or not. Oh, okay. So there should be. It's not actually. Uh, I'm not sure if I am getting the answer right here. I'll just come back to this. Basically, the answer should be around. Sorry, about 90%. I have also tried to check on how to get this answer. Firstly, I'm not able to find a decent enough classification. Maybe I would have gotten somewhere else wrong. 75%. Maybe I have to take two, subtract two from each side. So I have to subtract four actually here. So 37 times
So equal will
20.
be all the points, interior points, which are do not have boundaries connected to them. That's it.
Yes,
Yeah,
yes. So basically, we can do that
I guess.
and count the
Uh,
number of points.
yeah,
But yeah, whenever you don't have an interior point, it will be not sleeping. But that is the condition how it's
yeah, I
done.
get it. So I think that should be 90. I think.
Yeah, it will come around to 90. I'm not sure. I'm not getting the right answer right now. I couldn't. I was not able to get it earlier as well. I'll get
I
back
was
to you.
including the ones which were adjacent to the boundary. So
Ha ha. So yeah,
so
fine.
I guess yeah, you should get 90%.
Yeah, okay, fine. I'll come back to that too. Give a proper solution on that if one of the following classes. So, moving on to the next question: which of the following can be used to solve a system of equations Ax equal to q described above?
It's 2 and 3 because the first one is only for tri-diagonal, right?
Yes, it's only 2 and 3 because we need a matrix that is of this form and not of such a form. Whether since it's a 3D, it will be like this. So TDMA is used for only for solution of a tri-diagonal, which includes the diagonal and two and each element above and below the main diagonal. Question number 6: diagonal dominance condition is required for which of the following methods?
Uh, uh,
Basically, yeah,
one,
go ahead.
one and three, right? But 1 and 3, because one is iterative,
Yeah,
the second one is not. But I didn't
yes.
understand why TDMA requires diagonal dominance. Because
Uh,
that's not a TDMA is not a iterative process, right?
I mean, TDMA is any iterative method will require the use of a diagonal dominance.
Correct.
Yes.
But is TDMA iterative?
I'm not sure. Actually, it's not iterative. So
I, I, your lecture also says it's required. I couldn't figure out why.
actually, TDMA is just a special method of Gauss elimination. If you consider
Correct.
it
So
like
why
that,
it requires diagonal dominance? I didn't get it.
that's a good thought. Actually, it shouldn't be a condition for TDMA. I'll get back. I'll just check with Professor Srinivas Jayanti and get back to you because this statement is in fact quite confusing since TDMA is not an iterative method.
Correct. Correct.
It's I can we can make that as a it's like a special case of the Gauss
It's basically
elimination.
manipulating the matrix, isn't it?
Yes, yes, it's the special case of Gauss elimination
Yeah.
and not an iterative method. That's one of the questions you had asked, and I was
Yes.
not able to
Yes.
understand the question in the first place. Now that you have put this point for in the
Yes,
discussion over here. I'll just confirm this with Professor Srinivas Jayanti
please. Yeah.
because this statement should not, this answer should not make the right sense.
Unless I'm missing something, I don't know.
Yeah, yeah. I mean, I am not
Yeah,
exactly sure right now. So we can ignore this figure over here. This was from the previous week, apparently.
yeah.
So question number 7. Again, we are solving the equation Ax equal to b using the Jacobi method, and it's an iterative method. So which of the following conditions must be satisfied by the matrix A for the method to work?
So three.
Yeah, it would require the matrix to be non-singular, because any solution, any matrix that is non-singular is non-invertible, and hence we can
Yeah,
say that the rank, the it's an underdefined system,
yeah,
and a matrix A should be in the most irreducible manner so as to solve the iterative method fastest. And if it can be reduced, then the rank again it would be lowered, and we
yes.
can get an under determined system. And for all iterative methods, we require the use of the diagonal dominant condition. All of the rows must be diagonally dominant, and at least one row should be strictly diagonally dominant in iterative methods for getting the solution in iterative methods. Moving on to question number 8, the norm of the residual at the end of m iterations or n iterations can be evaluated as in which of these manner. So,
I think this
yeah,
is
sorry.
from the actually the next week, by the way. You know, this
Oh,
question.
I see. I mean, have I missed something out? Let me just take a look at that question number 9.
Eight, no, eight.
Uh, it-
It should be from week 10 actually.
oh, okay, okay. So you're saying that this question should have been in week
Yeah,
10, right?
yeah.
I see. Yeah. Because the sir had, I don't think professor had mentioned anything about the norm and
No,
the residual at the end, right?
I went ahead and looked and
I see.
looked at this.
Okay, okay. I thought I had made a mistake by putting it from week 10.
No, no, no. It's
Yeah, I agree with you. I completely agree with you in the sense that this is a bit too early. But I mean, I guess it can be said that people like
me for me it doesn't matter, because but I guess for the people
yes,
who are
yes, who are
young and
crediting, yeah,
who.
who are actually taking this
Yes, very, yeah,
graded will be having a
correct.
quite a confusion
Yeah.
here. But anyways, let's go through what the term norm means. Basically, when you solve the mth iteration by using the m minus one uh, m-1 set of data. So for an iterative method, you need an initial condition at x equal to x naught, which is used to find out the next iteration x1, x2, and therefore xm. So when you use the xmth iteration, we'll be using the values that is given in xm minus 1th iteration. And so for that, how do we decide that the iteration can be can is over, or when we are satisfied with the results that we are getting? For that, what we do is we substitute the values of ax, or if we substitute the value of the mth iteration as xm in b minus a times xm, where b is the constant vector. I'll just written, this is a vector, this is our square matrix we started with, and this would be our mth iteration, the solution after mth iteration. So when we put this back, we'll be getting another vector. We call that as a row, and this residual can be characterized by many different ways. Basically, we take the norm of the vector, and the vector norm is defined in multiple ways. The first norm is basically the sum of the absolute values of the vector. The second norm, this is norm 1. The second norm is basically the square root of the sum of each elements in the vector, and so on. And if you take the so if I take the third norm, it should be the cube root of cube root of the absolute value of the sum of the absolute values of the cube of the each element in the matrix. Similarly, if we go on like that, what would be at this point? I have to ask the audience, what would a norm of infinite value be?
0.
No, it
No?
won't be 0. See, if I think like this, suppose I have 1 minus 2 3. The sum of this will be 6 here. The square of the sum of 6 will be 3 plus 4 plus 1. That's sorry. The square will be 1 plus 4 plus 9 will be square root 13. Cube of this will be 1 plus 8 plus 27 under the cube root. This will be under square, which is equal to 35 cube root of 36. So we see that when we take a norm, this is 6, square root of 13 is approximately 3 point something, cube root of 36 is again 3 point, I think something again will come. I'm not exactly sure. One second, let me just find out that. This will be 3.6, and the cube root of 36 would come around to 3.3. So if we see this way, the infinite norm will be basically the max of the absolute value in that particular vector. So infinite norm corresponds to the maximum absolute value in that vector.
How come
So
we haven't, I mean, just a general thought. I mean, how come the RMS value was not considered for this as a norm?
this is the RMS value.
No, but there is no average, right? There.
Uh, it's not averaged, that's
We are only
correct, but
looking at root and square. We are not looking at
root
the
square
mean.
value, yeah,
Yes.
you can say root square value. Yes, yes. Um, so
Just,
average in
just
the
a
sense,
general question. Yeah.
yeah, we are actually averaging. We are not averaging. Yes, that's correct. Um, uh, we don't consider it, we don't necessarily, for vectors, what we have is a mathematical operation called as norm. These are all actually
Okay.
mathematical operations. Finding the norm of a vector, finding the length of a vector are all mathematical operations on vectors.
Right.
So the root mean square does not have a mathematical significance as is.
Okay.
So we don't consider that. So we do this operation instead. And
Yeah.
so therefore, any of such norms of any of the norm of the residual can be considered as a stopping criteria, or as a criteria for getting convergent, or ending the iteration. Therefore, largest value in the magnitude of b minus a xm would basically mean the infinite
Infinity.
norm
Yeah.
of
Right.
the residual. And this refers to the second point refers to the second norm of residual, but the third one doesn't have a particular significance in finding the norm of the residual. So the third statement is wrong over here.
Yeah.
Only the infinite norm and the second norm are shown as the first and second option respectively. Okay, moving on to question number 9. Which of the following is admissible as a stopping criteria with a successful solution for an iterative method for the solution of Ax equal to Q? The number of iterations is greater than a limit xk minus xk minus 1 less than a low limit for R variables, or residual less than a limit.
I chose residual. I just applied common
Yeah.
sense.
Yeah, this is the only what factor that generally is being taken into. Basically, even after 100 iterations, you may not get a particular convergent solution. You are not necessarily getting a proper answer with by setting the number of iterations greater than a limit.
Yeah.
We can't guarantee to say that. And similarly, if a solution is not getting convergent, we can't say that xk minus xk minus 1 is a low limit. Or even if it is, let's say, xk minus xk minus 1 may not give the correct answer for this, and such a low limit is basically undefined over here, and
Correct. Yeah.
therefore the only
So
correct answer,
subjective. Yeah.
yeah, the mathematical approximation, or we can quantify it using the finding the norm of the residual less than a limit, whether it
Right.
be a norm, an infinite, a first norm, second norm, whatever it is. A quantification can only be done through a residual.
Right.
And if xk minus xk minus 1, if it can be plus or minus, so let's say if in the first iteration I'm getting 5, or let's say in the first iteration I'm getting minus 5, the second iteration I'm getting plus 3, the xk minus xk minus 1 will be being 8 over here.
Yeah.
So that statement cannot be, that statement is wrong over here, and therefore we should always keep the residual less than a limit in this case. Okay, for the last question of the graded assignments of week 9, which of the following statements is or are true about the solution of linear system of equations? Ax equal to b with known coefficients. First one is, if Gauss elimination works, LU decomposition can be used. If Gauss Seidel works, TDMA can be used.
I guess it's only first. First
Yes,
one. Yeah.
if Gauss elimination works, then LU decomposition can also be used, because Gauss elimination what is basically the same thing as LU decomposition, but with a small difference, with the fact that for Gauss elimination we have A1, A11, A12, A13, etc. We have the matrix over here. We convert that to an upper triangular matrix like that, and in the LU method we have this A matrix over here, which is converted into the product of lower and upper triangular method. So this both upper triangular metrics are effectively going to be the same in regardless of the way we have done. It's just the factors that we have considered for the row operations, whether it be R1 changes to let's say R1 plus or minus k R2. This k is what determines the elements in the L matrix. So the operations that are done here will determine what's done in the L, and the final matrix of whether you solve by Gauss elimination or LU decomposition, the U matrix will be the same. And second point, if Gauss Seidel works, then TDMA can also be used. That statement is wrong, because TDMA is only for
Tridiagonal. Yeah.
tridiagonal matrix, whereas Gauss Seidel can work for any
Any.
convergent, or let's say diagonally dominant matrix. Okay, so we have come to the end of the graded assignments for week 9. We'll move on to the non-graded assignments, but before that, we'll take a short break, 2 minute break, and I just catch up in a couple of minutes, right? Okay, we shall resume if everyone's back.
Yeah.
Yeah, sure. So in the non-graded assignment, the effective, the initial part of the question remains the same for the three-dimensional network that's given. Whatever is we have started with is what has already also been there for the week 2, which asks us to solve the Laplace equation in a three-dimensional domain and with a central difference approximation we are discretizing it. So let's get back to whatever we were doing till now and answer the non-graded assignments questions for that. Which of the following equations is an approximate governing equation for this problem? So in the first term there is an unsteady term plus a convection term. In the second point there is an unsteady plus a diffusion term. The third term there is a diffusion with a source. In the fourth one there's a diffusion with a consumption. And that consumption term comes from e less than 0, and this would be the source, or this would be the sink term or the consumption term or whatever it is that needs to be called for the particular case. Now, among these questions, which of the following are appropriate governing equations for this problem? So we see that we need a Laplace equation of Laplace equation, and that from that we'll only get by solving either 3 or 4. If we solve the second one, which has an unsteady term, we won't be solving for the Laplace equation over here, and even in the first case it will be different from what is being asked in the main initial concept of the question. Okay, next one, Poisson equation is an example. Actually, the French pronunciation is Poisson. So, Poisson equation, what we speak here, is an example of what kind of a system. Poisson equation can be written as del square phi equal to 0, which can be expanded out like del square phi by dou square plus dou square phi by dou y square equal to 0. This will be in 2 dimensions.
So it's elliptic.
Yes, it is an elliptic. A hyperbolic equation looks like dou u by dou t is equal to minus a dou u by dou x. Uh, and a parabolic equation would be dou u by dou t equal to dou square u by dou x square with some constant, whatever it is. So, and it's not an equation of a mixed character, and you can see that it is clearly an elliptic equation that follows this manner. Moving on to the next question, for an interior point which does not consider, as stated here, uh, does not consider bound, let's say, how do I phrase it? Does not consider boundary points.
Oh,
Uh,
interior is all non-boundary points, no?
no, no. Interior is all points that does not have a
Oh, I see.
boundary,
Okay.
does not have a point with a boundary point. I mean, how
As a
do I
neighbor,
say?
as a neighbor.
Yes, yeah, as a neighbor. Yes, that's exactly the. Yeah, that's the exact phrasing. So we have seen earlier that there will be where is that the first question that we've solved. We see that there will be uh, a total of 7 elements, and out of that 7 elements, all these terms will be a known quantity if and only if the point is a non-interior point. If it's an interior point, all of this will be unknowns, and therefore an unknown and an interior point will have the number of non-zero coefficient to be 7, as can be seen here. And they've asked us to find the number of equations to be solved. I think there is a difference in the question that was asked. Let me just take the question over here.
Just a 2D, no?
Yeah, that's where it comes from. So we are considering the two-dimensional form of the equation, am I right? Yes, with 20 and 30 intervals. Okay, it's a 2D problem with, I had forgotten to write down the entire statement over here. I was assuming it was the same, but in fact we are dealing with a two-dimensional equation with 30 and 20 intervals in let's say x and y direction. So therefore there will be 31 times 21 uh, grid points, and total grid points will be 31 times 21, out of which there will be 21 it's 1 second. Yeah, so there will be out, so we have this 31 times 21 total number of grid points, and out of which 31 times 2 will be the boundary points. We can write that a little bit clearly. 31 times 2 will be the boundary points in, let's say, x. 21 times 2 will be the boundary points in y. Therefore number of equations will be equal to number of unknown grid points, which is equal to
And
the
21, 2 will be already accounted for in 31, no?
I'm sorry, what was that?
No, once you take 31,
Hmm.
so when you come to y, it will come down to 19, isn't it?
Um,
Because you're
yeah,
taking the
yeah.
corner point.
Yeah, we generally don't speak about tear that corner point. We generally tend to ignore
Yeah,
it in the whole sense as it is.
yeah,
But
because
yeah,
it's just one or
we
two.
can,
Yeah,
yes,
yeah.
yes, we can write this as 19 itself.
19.
Yeah, we can do that. Exactly. Yeah, we should do that in the right way. Yeah, 31 times 2 minus 19 times 2. So we'll get this to be 550, exactly 500, or roughly 550, depending on how the analysis was done. So some of these statements in one of the assignments I had done during the lectures here, what the professor told was to take the average at the corner points.
Mm.
So while solving a CFD problem, suppose I was solving the temperature at this would be at the average of temperature over here and here. So these are all manipulations that we need to think about and work with. So if we can avoid the corner point temperature here and here, and basically put that equal to the temperature at the x or the y or whatever it is, or take the average or however we see fit. We do not deal with such a corner point in such evaluations that we have seen.
Anyway, with a large number of grid points, I mean, just 2, 3 points hardly
Yeah,
matter.
exactly. It may making a very small change anyways. We can account for that as well. Then the percentage of elements that have a non-zero value will be. So in the coefficient matrix, we saw that there will be 550 elements over here, out of which a maximum of 7 elements will have uh, a non-zero value. Therefore, the answer will be, I think, 7 upon 550 will be the number of non-zero values. times 100, and we'll get this to be around, I think, 1.3%. And I am not, I think the answer will come to
Yes.
C. Please let me know if I have made a mistake anywhere or in this.
That's correct.
Yeah, it'll be 1.27 percentage. I just did the calculation. So it'll be around 1 percentage of the elements will have a non-zero value uh, in the coefficient matrix.
So these are all the interior points, right? Or,
Um,
or,
this
or
this
all
this is
non-boundary.
oh no, this is for a
Uh,
row which has which is considered as an interior point. A row that comes from an interior point will have maximum 7, and a row that has does not have this will be around 3 by 550 into 100. So
okay.
that will be much lower than that.
So these the adjacent points to the boundary,
Hmm.
they are what? They not guaranteed to have non-zero, is it?
They are not guaranteed. Yeah, that's what is correct. So so let's consider this as the two-dimensional case. 1 2 3 4 here, 1 2 3 here. So this this points over here,
Yes.
1 2 3 4 5 6 7 8 9 10. These 10
Uh,
points will consider the boundary points associated with that, and thereby will have less than 7. It will be having 5 if you are considering these points.
ah,
We'll have 3 if they are considering these points, and we'll have 7 if we are considering these 2 points over here.
right. Okay.
Yeah, so we have to basically multiply this times 2 plus this times, let's say, 1 2 3 4 5 6. So this times 6. No, this will not be 3, this will be 5 over here. And 4 times 3 by 550 into 100. And average that out to get the final answer in the right way. I hope this what I said right at last made sense, because what I'm saying is the total number of elements in the matrix will be written out like this. So there will be 2 times 7 plus 6 times 5 plus so in each row there will be 550 elements, and there will be 7 elements for these 2 points. There will be 5 elements for these 6 points, and there will be 3 elements for these 4 points. So we have to add them all up and divide it with the number so as to get the correct answer over here. Okay, so we have completed the non-graded assignments. Yeah, I think this is question number 5 over here, not 4. Huh. But we have completed the non-graded questions that were there for the non-graded assignments for week 9. What I have is a couple of more example questions which ask us to perform the LU decomposition and Gauss elimination. So we'll take a minute's break over here, see, and we'll move on to I have like 4 questions which deal exclusively with the solution of or how to solve LU decomposition and Gauss elimination. Because I saw that in the lectures that were given, all of the questions were related to how it can be solved rather than how to solve it. So we'll take a minute's break before I come back to this. Again, this particular problem is just mathematics. It won't be dealing with any CFD technique over here. So you can see that all of these questions are very straightforward from a mathematical sense, where we use Gauss-Seidel. In this question, we have used Jacobi iteration, LU decomposition, and Gauss elimination. and also a successive over relaxation method uh, over here. So we'll take a minute's break and continue with these example questions.
Sure.
we use that to find our number over here. It will be 0, it will be again 0, 0 minus 0 will be 0, 1 plus 3 times minus 1 by 3 will be 0. Similarly 3 plus 4 times 1 by 3 will be 13 by 3. So we'll get that over here. Similarly, we'll get 5 plus 5 by 3, which should be equal to 20 by 3. If I think I have made a mistake again somewhere. Let me just go back and evaluate.
Why can't we do 3 3R3 plus R2?
Yeah, it'll be the same answer. It doesn't matter if you are doing 3R3 plus R2 or R2 plus R3 plus R2 by 3.
So you're getting a
So
fraction, no?
yeah, okay, we can do that way only. 3R3 plus R2.
Yeah.
So we'll be getting 0, 0, 9 minus 4 is 5, and
Yeah.
we'll get 15 plus 5 as 20. I think I have made a mistake somewhere in the second step because I shouldn't get this
You
answer
shouldn't be
right.
getting a fraction somewhere, yeah.
Hmm. Yeah, so let me just go through what I have done. So R2 minus R1 will be 0 minus 3, 4, 5, and R3 minus R3 tends to R3 minus 2R1 will be 0. One second. So it will be 2 minus 2, 3 minus 2 is 1, 1 plus 2 is 3, 7 minus 2 is 5. Okay, let me again go ahead and solve this. I'll get the value of x3 to be 4 and minus 3x2 plus 16 to be 5. So minus 3x2 should be equal to 5 minus 16 is minus 11. I'm not getting a right answer over here. I don't know where I have made a mistake. Have I copied it wrong? 2, 3,
I,
1, 1 minus 2. Oh, sorry.
it's okay. I mean, we got the
Oh, okay. Yeah,
process.
I
Yeah.
think I have copied the question wrong again.
Yeah.
This whole statement is wrong. There is a minus 6 over here. It's my mistake. So it's not the answer that's corresponding to what I've written, but I'll get an answer over here. So I'll get let me finish this off in my way only. Then I'll get one. It'll be minus 10 over here and some other value over here. So this is okay. So this will be 5. Then I'll get a value 5, or 5 minus 15 minus 10 will be 5. 9 minus 4. Yeah, this is what I am getting. So I'll get x3 to be 1. 7 minus 6 times 12 will be minus 5. So yeah, minus 5 plus. Just 1 second. I'll be getting a minus 1 for this. X2 will be. I think I made a huge blunder over here, and sorry. This will be x1 by back substitution. X1 will be 1. I think I've copied the entire question wrong. So let's. I think I'll come back to this after. Let me just revise my notes and come back to this after the end of the class today. So we'll move on to the next question because whatever I've done earlier, I think I made a lot of blunders. So 6, 2 plus 2x3 to 12, 3, 8 minus 2 25, 1, 1, 4, 6. I guess this question will be correct. Again, we'll do the next question. 5 minus 1, 2, 3, 8 minus 2, 1, 1, 4 times x1, x2, x3 to be equal to 12 minus 25, 6. Okay, so we've been asked to do the Jacobi iteration over here, and for a Jacobi iteration what we do is we write x1 to be we hold x1 over here and write the terms in terms of x2 and x3. We hold x2 over here and write the equation in terms of x1 and x3. We hold x3 over here and write the equation in terms of x1 and x2. So we can write this by saying as x1 as 12 minus or 12 plus x2 minus 2x3 divided by 5. We can write x2 as minus 25 minus 3x1 minus or plus 2x3 divided by 8. x3 to be equal to 6 minus x1 minus x2 divided by 4. So what we do here is we start with an initial iteration. Let's initial guess. Let's say our matrix x naught is given as 0 0 0, and we have to perform, let's perform 2 iterations over here for the sake of time. So let me write down what all we need to find. We need to find the iteration number x1, x2 and the residual. Let me write this table over here, which is iteration number x1, x2, x3. Let's take the infinite norm of the residual over here so that we have an idea of what the residual is. So we have an initial guess over here given by 0 0 0. We substitute in this equation for x1, we substitute in this equation for x2 and this equation for x3. We'll get a value for x1, x2, x3. We find out the norm over there. Then with the help of that particular value of x1, x2, x3, we find the next iteration at x2 using x1. So we know the x values at the 0th iteration. Let's find out the values at the first iteration. So it will be x1 should be 12 plus 0 plus 0 by 5, which is equal to 2.4. Then x2 should be equal to minus 25 plus 0 plus 0 by 8, which is equal to minus 3.125. And x3 to be equal to 6 minus 0 minus 0 by 4, which is equal to 3.5, 1.5 or 3 by 2. And the residual of this is found out by substituting in the form b minus axi, which is done by finding out the values of by substituting the value of 12 minus 25 or 6 minus 5 minus 1 2 3 8 minus 2 1 1 4 times the evaluated value 2.4 minus 3.125 and 1.5. So this is b minus a times xi, and xi is the first iteration over here, and we find the maximum value over here to be the infinite norm as the condition for, let's say, convergence over here. And for this question we can assume that if it's converged, if the infinite norm is let's say for our case infinite norm is less than 3. So in this case, if we are solving for the residual norm, we'll get the residual as a matrix 0.125 comma minus 4.2 comma 0.725 transpose, since it's a vector. So we see that the infinite norm will correspond to the largest absolute value of the largest value of the absolute among the elements of that vector, which corresponds to 4.2. I've already done the calculation so as to save some time over here, but we can confirm this particular case where we get the infinite norm of this particular matrix given by b minus axi to be 4.2. Then we go on to the second iteration. We substitute the values of x2 and x3 as 3 point, minus 3.125 and 1.5 to find x1. So it's 12 minus 3.125 minus 3 will come over here. Minus 2x3 will be minus 3. So divided by 5, and we'll get that value to be around 1.175. Similarly, for x2, if we have to substitute minus 25 minus 3 times 2.4 minus plus 2 times 1.5 divided by 8, we'll get minus 3.65. And x3 we can get it by 6 minus 2.4 minus 3.25, 3.125 divided by 4, we'll get it as 2.118. Similarly, if we calculate the norm or the residual, the residual at this iteration b minus axi, where the b remains the same, the a matrix remains the same, only xi will change at, and we'll have to use these values over here. We'll get the following vector as the residual vector as minus 0.89, minus 2.69, and I think it will be 1.75. Therefore, the infinite norm over here will be equal to 2.69, and this statement is converged if the infinite norm is less than 3. Therefore, we can go ahead with this particular values of x1, x2 and x3. So ideally, if I solve it the other way, I'll get the values of x1 to be equal to 1, x2 to be equal to minus 3, and x3 to be equal to 2. So when I solve it using a method, an iterative method, I can see that it becomes 1 minus 3, 2. And in the next iteration, I have already written down the answer. Just make a note of that. You can just confirm this one. We'll get it as 0.9975 minus 3.1453, 2.11875, and we'll get the infinite norm or the max value to be equal to 1.4. What we are seeing is that the residual keeps on decreasing with the as the iteration increases, and that can only be done for a diagonally dominant matrix. If we don't have a diagonally dominant matrix, we won't be able to get this particular pattern. And we see that the solution asymptotically reaches, the iterative solution asymptotically reaches the actual value of the system, and can this, for this particular case, we can use Jacobi iteration to find the solution. Although most of these calculations I've performed it, anyone can verify these answers, and just let me know if I've made a mistake somewhere.
If you can just show the matrix, the
The
original
initial,
one, the original, yeah, 5. 1 second.
yeah, sure.
Can you just enlarge that a little bit if you don't mind? Yeah, hold on. Yeah. 5 minus 1, 2. Eight minus 2. I'm getting 1 minus 3.15, 2.12. The third iteration.
Yeah, that
No,
would be
hold on, hold on. What are your seed values 000, is it, or
Yes, yes.
something
My
else?
initial guess was 000.
000. I am getting third iteration 1 minus 3.15 2.12.
Yeah, that's close enough. Maybe
Yeah.
due to truncation error, that could have
Yeah.
been the reason. But yeah, you can see that the solution does in fact come to the original solution asymptotically, or when the iteration has gone to infinity or something like that.
Oh, it's just because of your precision. That's it.
Yeah, I have
Then,
taken like instead of 3.65,
yeah,
I
yeah,
would
yeah.
have given the value of 3 points instead of 1.68. I would have used some other value. I think this value I've mentioned here is wrong. It will be 1.68125.
Oh, I got the exact same thing.
Yeah,
0.9975 minus 3.1453 2.1188. Yeah, perfect.
yeah, fine. Then we'll move on to we'll finish off one more question before hopefully before the time ends at least, the one on a Gauss Seidel method to find the answer. So this is an application type, but is not of CFD type question. It's a general mathematical question or a physics related question where the upward velocity of a rocket at three different time instances given in the table, and this is time and velocity as this is velocity as a function of time, where we have 106.8 at 5 seconds, 177.2 at 8 seconds, 279 at 12 seconds. And the data that's given here, the velocity data may be approximated as a polynomial in time as this particular equation given by a1 t square plus a2 t plus a3 in this particular interval, 2 less than t less than 20. Now we are asked to find the rocket velocity at 15 seconds using Gauss Seidel and perform two iterations. And they've also given us the initial guess over here as well. So Gauss Seidel refers to is basically same as Jacobi method, but with one small variation. We just have to use the new xi values, let's say xik values or xik plus 1 values for finding xj k plus 1 for every j less than, or sorry, I less than j. So whenever you are doing the finding out the values for xj as given in this particular Jacobi method, for finding out this particular one we used this set of data. But according to Jacobi, for finding out x2 you use these three data. So we can start by finding out what the question has asked, because what is given may seem like a nonlinear or a quadratic formula rather than a system of linear equations, but is in fact actually a linear equation in A1, A2 and E3, A3. So when we solve this, we'll get, when we put the conditions of time and velocity in this particular equation, if we substitute 5, we substitute 106.8. When we substitute 8 here, we substitute this value, and 12 and this value. And we'll get three equations to find out A1, A2 and A3, which is not basically a velocity versus time. We just have to find out A1, A2 and A3. And let me start by substituting the values of t equal to 5 seconds to be 25 A1 plus 5 A2 plus A3 should be equal to 106.8. The second value of time to be 64 A1 plus 8 A2 plus A3 to be 177.2, and the third point is 144 A1 plus 12 A2 plus A3 should be equal to 279.2. Just one second. Yeah, cool. Yeah. So we now find out uh, now write down what a1 is in terms of a2 and a3 from the first equation as 106.8 minus um, 5a2 minus a3 divided by 25, and a2 to be equal to 177.2 minus 64a1 minus a3 divided by 8, and a3 from the third equation as 279.2 minus 144a1 minus, sorry, this should be 12a2 divided by 1. Now we have these three equations. We start with the initial guess, a naught to be equal to 1, 2, 5, and we can see how we can find out the values over here. So let this be the iteration number. Let this be x1, x2, x3, or in this case particularly it's a1, a2, and a3, and this to be our usual infinite norm of the residual. We substitute 1, 2, and 5 into this equation, and for the first iteration, can I get the values from any of the members attending the class? I mean, if you can tell me what a1, a2, and a3 is after the first iteration, basically to substitute the values of 2 and 5 over here, we'll get a1.
Uh, I'm getting 4.27 minus 12.03, 191.66.
After the first iteration,
Yeah, the seed value is 000, no?
the question is mentioned as 125.
Oh, the seed value,
Yeah, yeah,
uh, 1, 2, and 5, huh?
yes.
Oh, okay, hold on. I'm getting 3.67
Yeah,
minus 7.85
yeah.
and minus 155.36.
155.36. And what would be the infinite norm? If have you found that?
Oh no, that
Okay, that requires intense calculation. So I'm
I know.
gonna,
Yeah, it
yeah.
requires.
So I'm gonna give the answer directly. It's gonna be 209.6 something.
Okay,
So what about the second iteration?
12.06
12.06. Yes, that matches.
minus 54.88
88, and
minus
a3
798.
minus 798 point something.
Is this
And we
diagonally dominant?
exactly what I'm coming to. So we see,
Okay. Yeah.
so what we see here is that the infinite norm over here will go to 2000 something over here,
Uh,
and in the third iteration we'll see a value that's even more bigger over here. So the point I wanted to make is, in this calculations we won't be able to get a converging solution,
right.
uh, mainly because the diagonal dominance is not satisfied. So we can't use any iterative techniques over here, and we have to rely on solving it directly rather than the other way, the iterative way. So this is regarding how non-diagonally dominant matrices come across in Gauss-Seidel method, and we see that the correct answer for A1 would be, we see 0.2982 should be equal to 19.09, and A3 should be equal to 1.086. This is the true values, and we see that we can't find them out. They are not even coming close. If
Yeah.
3 and 12 and are not even close to 0.29, and this are in fact diverging everywhere. So we can't use an iterative techniques for this particular question. We'll just do one more question since we have around 10 minutes time. We'll quickly see how, or I may not even be able to finish, but we'll see if we are able to find out what the values are. We are supposed to use successive over relaxation method for finding out the answer for solution of this particular set of equation given by 3x minus y plus z equal to 1, minus x plus 3y minus z equal to 7, and x minus 3y plus x minus y plus 3z equal to minus 7. So I start the same way, and I'm gonna use a couple of things. Let me write down what I'm gonna use over here. I'll write the initial guess of x naught as 0, 0, 0, and I'll use the relaxation factor omega to be 1.25. I have not shown that in the question over here, but I've used this one to calculate, to perform my calculations. So when I try to solve it over here, how does the successive over relaxation work? It's basically it's an in between of that of Gauss-Seidel and Jacobi iteration. And when we use Gauss-Seidel, we have to use a new one. When we use Jacobi, we use the values of the previous step. And for successive relaxation, we use a weighted average of the ones that are found out from each of them. So I write down the equations as x as 1 plus y minus z by 3, um, y as, sorry, it should be 7 minus 7, once again, yeah, 7 plus x plus z by 3, and z as minus 7 plus minus 7 minus x plus y by minus by 3. Now what I do here is, for successive over relaxation, I multiply this with a factor omega, and I multiply the suppose this is at k plus first iteration. I use the kth iteration values for yz and xz over here, the k plus 1th iteration for x and the kth iteration for w over here, and both of them at the k plus 1th index over here. And I multiply or add and multiply with 1 minus omega for the value at the kth iteration for the corresponding uh, element over here. So again, we write down what is the table and just substitute back in. I'll do the first iteration and we can confirm how the answer comes out. So here I'm not found out the residue, and I'll just write down how we found out the x1, or in this case the x, y and z over here. So I started with the initial guess of 0, 0, 0 and weight fraction of 1.5, or the relaxation fraction of 1.25. So this is 0, 0, 0. So it will be 1 by 3 times 1.25 plus minus 0.25 times 0. So it will be 1.25 by 3. By 3, which comes out to 0.4167. Now I'll substitute this newly found value of x over here. So it will be 7 plus 0.4167 plus and z will be 0 divided by 3 times 1 times 0.25, sorry, so times here again omega will come. I forgot to write the omega over here, times 1.25 minus 0.25 times 0. So I'll get that to be approximately around 2.743, and similarly I'll get the Z to be around minus 1.6. So in the second iteration, I'm just gonna write down the values because I don't know if we'll have enough time to solve it. We have to use this, sorry, this values over here in YZ over here, and 0.4167 over here. I'll get here as 1.497 and 2.188 and minus 2.228, and in the next iteration I'll get 1.05, 1.88 and minus 2.014, and by the time I reach my ninth iteration I've just taken this directly from one of the calculators that I've used to be around 1.0004 or something. It will be 1.9954 and minus 2.006 or something. So we can see that this has in fact converged to the actual solution that's given by 1, 2 and minus 2. So therefore we have found out how to use successive over relaxation method to find out the particular value of this one. Now one exercise I would suggest is to take any of the questions that I have given, either this one for here or Gauss Seidel. Or Gauss Seidel we can't use iterative techniques, but we have used Jacobi iteration over here, or the Gauss Seidel Gauss elimination LU decomposition method over here, and to compare its residual, the norm residual, for just take one particular case, maybe the third question, and compare the infinite norm and see how well it can decay, or how well it can, how quickly we can get the answer, how quickly we can get it convergent solution out of all the three methods, considering that considering a single question over here, one of the questions over here. So yeah, please feel free to verify these answers and let me know if I made a mistake. Um, I think we have used up all the time for today. If you have any other doubts, I'll be there for a few more minutes if you want me to explain any questions or any other topics in interest.
Just that outstanding question from my side. Yeah,
Sure.
yeah,
Okay.
that's it from my side.
Okay.
Yeah, good night.
All right. Good night then. Yes. Thank you for your time. I think I'll end this session right now.